solve the Arrhenius equation to find out the pre-exponential factor and the activation energy using the Arrhenius equation. And you can see the Arrhenius equation on the screen right now. Is k equal to a, that is the pre-exponential factor, exponent exp to the power minus ea, that is the activation energy, divided by r, that is the gas constant, and t is the temperature. And as a chemical engineer, we should use the temperature in absolute unit like in Kelvin, right? So to get the value of the activation energy and the pre-exponential factor, we need some experimental data sets from the data set, basically in the form of k and the temperature, as we know. So this Arrhenius equation is the relations between temperature and the reaction rate constant. So usually what we do, we take the E base log of the Arrhenius equation, and we have these things. You can see it here, I hope. So it is ln Ka equal to ln A minus E divided by R T. And if we try to plot it, it will give a straight line. You can see in the graph here, in a semi-log plot, this is definitely, we can plot it as a normal plot. We'll see it after a few minutes, hopefully. So we have in y-axis, that is the value of k, as it is a log axis, the y-axis is log. So it is basically plotting ln k, and in the x-axis it is 1 upon k. This is the normal axis. It is a semi-log plot. So we are plotting 1 upon k in x-axis and ln k in the y-axis, and you can see the Arrhenius equation will give us the straight line, and the line slope will give us the value of Ea by r. Right, you can see the slope is minus Ea by r, and the intercept will give us the value of ln A. Right, and if we know this slope and intercept, we can know everything. Right, so let us go to the problem statement. So you can see the problem statement that we are describing in the example in the book and also in the class notes. Right, so the example 3.1 you can think of. And we need to find out the activation energy, the Ea, and also the pre-exponential factor of benzene diazonium. This is a dissociative reactions that will make chlorobenzene and nitrogen. It's a simple reaction, and we have the kinetic data. Basically, it's an experimental data. We will not get the K value directly. Usually, we get the rate value. We calculate the rate value, and from the rate value, if we know the rate law, we can calculate K value, but we are not talking about that thing right now, right? So we have the, let's say we have the K values with its corresponding temperature value. So with different temperature, we have different K values. That is the Arrhenius equation. It gives the relation of temperature with K, right? And K is really gives you the rate law. So the higher the, we know that if we increase the temperature, the K value will increase, and also the increase the reaction rate, and we have faster reaction rate. Something like that. We are seeing it also here. With the increase of temperature, the value of K is increasing. That makes that, okay, the data looks very authentic. And if you look into the unit of K, that is in second inverse, that means that it is a first order reaction. So if you can remember the units of K, or reaction rate constant, right? So we know that the reaction can be a 0 order, first order, second order, third order, and so on. Right, usually these three things we have learned about the units, and how if we have a time inverse unit in a reaction rate constant, it is a first order reaction. Right, so we will use this experimental data to find out the value of the activation energy, which is Ea, and the pre-exponential factor, that is A. So now we will move to our Excel sheet. Hopefully you can see the Excel sheet, and I tabulated in the Excel in the way, right? You can see the temperature first. This is our X values, and then the Ka. This is the reaction rate constant, and the y-axis it should be right. Now we need to formulate the values in terms of the Arrhenius equation. That is, in x-axis it should be 1 divided by T, 1 by T, and in y-axis this will be our x-axis, and in y-axis it will become ln Ka. Right, so this will be our y-axis, and we can just it is very easy to have the manipulated calculation data points in Excel, but also you can make a table like this using your calculator. So it is the inverse of the first column. You can think of the temperature column, right? So it is equal to 1 divided by, you just select the column and just press it, so you'll get the inverse of temperature value directly, and you can just copy and paste. Also you can do the same things for the other boxes, right? So you get all the temperature inverse value. Similarly, we can take the y value as logarithm, so it's equal to ln the formula. I hope you know how to get the ln in Excel. Just select the k values if you want to make the logarithm, close the bracket and press enter. So you'll get a minus. Definitely it is less than 0, sorry, it's less than 1, so it is a negative value of the ln. So then again you can just copy the formula and paste it in the other boxes. So now we have our table ready for calculating the Arrhenius equation, or plotting the Arrhenius equation in ln Ka, that is y-axis in our case, ln Ka, versus the x-axis, that is 1 upon t. Right, so these are the two values, x and y. If you can just check it that I put x big at the first and y that's followed by the y, right? So now we will try to get the plot. Now we select the insert tab in Excel, select the charts, and we will select the scattered plot, right? Okay, I make a mistake here, right? So first of all, I need to select the data points, right? First of all, select the data points, then insert, and then you select the scattered data points, right? So you'll see it here, right? So that's very difficult to understand what it is going initially, right? So definitely this is the y-axis of us, and this is the x-axis. So we can just think of our minimum value of y-axis is this one, minus 7.7. So we can choose, we can shift this line that crosses at 0. Usually in Excel we have the cross point at 0, right, and intersect point basically. So we can shift these things, and I hope you know how to manipulate these data points. This is just simple things. So we can just, this is a plot of Arrhenius plot, so we can just change the name of title of the plot, right? Just write down the name like this, right? So, and also you can just select this thing and text. You can see that if you select the column icons here and axis option you select, and you can see it here. I hope you can see it in the axis options. It is axis value. So vertical axis crosses, right? So it is basically, it will not help us. Basically just leave it like this, because we have to shift the y-axis thing. So just select the y-axis, so the axis value at 0, so we need to just make it minus 8, right? So you can see that the x-axis already shifted to things, right? And the maximum value, you can see that it is minus 8, just to have a very nice look of the graph, nothing else. And the minimum value you can also choose minus 4, so it looks a nice plot things, right? So you can also change the font size. You can just select the graph, like say, just select, and the graph is selected looking into the border, right, with some circles here. So you can just change the font size, it is changed. Also you can do lots of other things, and if you want to give the axis titles, so you can go, I think, the format, sorry, design, add chart axis title, so you can have primary horizontal, as you can see that you can write down here as this is inverse of temperature, right? It is 1 upon Kelvin, right, the unit. And also we will have axis title and vertical one. So this is basically, this value is ln of k directly, right? So we can write down ln of k. So this is our plot. So this is the Arrhenius plot, and looks like straight line if you just use your eyes, right? But we need the slope of the line. So you draw a line and try to find out the slope and intercept from the line, right? So what we do here, we use the function called trend line in Excel, right? So you just select all the points. Just if you just select a point, select a data and just click the mouse on it, and then left click on your mouse, sorry, right click on your mouse, and you can see the add trend line. If you after selecting the data, press the right button of your mouse, you'll see add trend line, and you will have the options, and you select the linear line. Now you have to do two things. You need to display the equation on the chart. It is a straight line, so y equal to mx plus c, something like that, and also display the r square value on the chart. These are two things you should select. And I'll just, let's see, I can change the format a little bit. I'll just shape fill completely, so you can see just now our work is done basically with the plotting stuff things, right? So you can see that the equation is y equal to minus 14612 into x plus 38.928. so that is our equation, right? So if you can remember our Arrhenius equation, it is ln k. I'll just try to write down here, ln k is equal to ln a minus e, just put a bracket to have a better understanding, e by r into 1 by t, right? Something like that. So you can say that 1 by t is our x. So e by r is 14612. But if you just try to compare things, so we have our e by r equal to, and we have a negative value, so negative value will cancel out from there, right? So it's a negative slope, so you can just write down 14612. So that is E by R. So the activation energy E will be E by R multiplied by R. R is a gas constant, right? So we can have, equal to, choose the value of E by R multiplied by, here we want to use the joule per mole, so we can use 8.314 unit, right? So we can have directly the value of E in terms of joule per mole, right? So now if we want to convert it into kilojoule, we'll select the title, so select the value of E divided by 1000, we'll get the value in kilojoule per mole, right? So this is how we can calculate the activation energy. Now if we try to calculate the activation energy in terms of calorie, what we do, we just multiplied it, just show you here, we just multiplied it with 1.987, right? Almost 2, so it will be calorie per mole, the unit, right? And also it will be, if it divided by 1000, it will be 29, right? So it will be kilocalorie, kcal per mole, right? So you have two options, either joule per mole or calorie per mole. Now we have to find out the value of A. So we know that ln A equal to, value is 38.925, 38.925, right? So that is our ln A. So if we try to find out A, then it will be exponential, exp to the power 39, sorry, I have to press the equal sign, exp bracket and select the data 38.925, close the data set, and you will get the value of 8.033 into 10 to the power plus 16. And we know that the value unit of A should be the unit of K, and if you can remember, the unit for this data set for this reaction is second inverse. So the A value should be, the unit of A should be second inverse, or 1 upon second. If you can write down like this, okay. I hope you understand how to calculate it, and the recording is going to finish. And I'm very pleased that we can finish this problem, and hope you can understand these things. Please practice. It is very easy. And in the exercise, we give you the